Hi everyone. In the last video, we introduced these objects called vectors. Now in this video, we are going to talk about operations that we can do on vectors. In particular, we're going to talk about addition, subtraction, and what's called scalar multiplication. So first, let's start with addition. Here we have two two-dimensional vectors u and v. Let's do addition, u plus v geometrically using these arrows. Then we'll talk about what that means algebraically in terms of components. When we add two vectors geometrically, one way to do that is to use what's called the tip to tail method. Using this method, what we do is start with the vector u, and the tip of u is going to be connected to the tail of v. So this is what that looks like. And to get the actual sum of u plus v, in this new diagram, what we do is to draw another arrow from the tail of u to the tip of v, like this. So this black arrow gives us the sum of u and v. Now let's think about what that means in terms of components of u and v. Look at these diagrams carefully. You can see that the components of the sum vector u plus vector v are given by the sum of corresponding components of u and v. So this is what we get. The first component of u plus v is going to be given by u1 plus v1, and the second component of the sum is u2 plus v2. So for a quick example, let's try to add two three-dimensional vectors. Say that vector u is going to be -3, 1, 5, and vector v is 2, -4, 7. Then, what the example is telling us is that we just simply need to add the corresponding components. So the first component of u plus v is going to be -3 plus 2. Second one is 1 plus -4, so 1 minus 4. And 5 plus 7 for the third component. So then we get -1, -3, 12. In section 9.2, it showed you another way of coming up with u plus v geometrically, so take a look at that. Next, I want to talk about subtraction of two vectors, but before I do that, I do need to introduce the idea of the negative of a given vector. This is really a simple idea. The negative of a given vector is the vector that has the same magnitude as the given vector, but points in the opposite direction. So for this vector that you see on the screen, the negative of vector u is going to look like this. And we are going to denote it by -u. And you might be able to guess what the components of this vector might be, but it's exactly the negative of each components of the original vector. So for a quick example, if I'm given a vector v, and I'm going to use another three-dimensional one for this, that is given by 5, -2, and 1, for example, then the negative v is going to be -5, 2, and -1. Using the idea of negative of a vector, now we can define subtraction. Given two vectors u and v, we define u minus v, so u minus v, to be the sum of u and the negative of v. So we can actually find out exactly what this is going to look like in terms of components, right? So u is u1, u2. Add to it the negative of v, so that is going to be negative v1, comma negative v2. So the components of u minus v, just like the sum, now in this case it's just going to be the difference of corresponding components of u and v. Of course, order matters, right? U minus v is not going to give us the same thing as v minus u. Now let's do the subtraction geometrically. Suppose that we have these two-dimensional vectors. Since we already know how to add two vectors using arrows, we can simply add vector u plus the negative of v, right? So this is what we get. Here is vector u, and we put the tail of negative of v to the tip of u. So it's going to look something like this. So u minus v is going to be this black arrow like this. Now let me show you another way of coming up with u minus v. For this method, what we do is to put the tails of both vectors together like so. So here we're putting the tails of u and v, not u and negative of v. But when we do that, and if I draw another vector from the tip of v to the tip of u, we get exactly the same vector that we got before. So this is another way of trying to find u minus v geometrically. Now let's talk about scalar multiplication. When we multiply vectors by scalars, they are called scalar multiplication. And for us, scalars are going to be real numbers. So for example, suppose that k is a real number and u is a vector whose components are going to be u1 and u2. So this is a two-dimensional vector. And for this, the scalar multiplication k times u is going to be defined by k multiplied by u1, u2. So we are going to multiply each component by k. So the definition of scalar multiplication in terms of components are going to be like this. So for example, if I have vector u that is 2, -1, 0, and if I multiply this vector u by the scalar 3, then we are multiplying 2, -1, 0 by 3, so we get 6, -3, and 0. So now, what does this actually do to the magnitude of the vectors? Let's think about that. If we take a look at the magnitude of k times vector u, well, we know that this is going to be the square root of the sum of the squares of components. So we get ku1 squared and ku2 squared. But factoring out the k squared from both terms inside the square root, we get k squared times u1 squared plus u2 squared. But you know that the magnitude of k can come out of the square root. So since we don't know if k is positive or negative, let me put the absolute value here. And that times the square root of u1 squared plus u2 squared. And you know what that square root expression is, and that's exactly the magnitude of the original vector u. So you get this expression. So what the scalar multiplication really does is to stretch the magnitude of the original vector by the factor k, right? And of course, if it's negative, then it's also going to change the direction of the vector u as well. But with this expression, I think we can look at the geometric interpretation of the scalar multiplication pretty easily. So suppose that this is the original vector u. Then let's take a look at what 2 times u might look like. And what that means then is that the direction doesn't change at all, but the length of vector u is going to double, right? So this is what we get. So if this is vector 2 times u, then the length is going to be exactly twice as long as vector u. And if I want to get 1/2 u, then this is what we get. So this vector has the half the length of the original vector u. Now for the last example, let's try to combine all these operations that we talked about in this video. So consider these three three-dimensional vectors, and let's try computing this. 5u plus 3v minus 2w. So we have 5 times the vector u, 2, -1, and 5. Add to it 3 times the vector v, so that's -5, 2, and 3. And minus the twice of 2w. Now we can think of this as adding the double of w, but let me just write as -2 times 1, -2, 4. Okay, so this is going to give us 10, -5, 25, plus -15, 6, and 9. And again, looking at this as the adding -2 times the vector w, we get -2, 4, and -8. So by adding all corresponding components, we have 10 minus 15 minus 2 for the first component, -5 plus 6 plus 4 for the second, 25 plus 9 minus 8 for the last. So we get -7, 5, and 26.